So number 2. So you have a different function. This time, I don't know, looks like this, I guess. This is, we'll call this g. Okay. And I want to know the area between the same interval, a to b. Right. It didn't really matter. You would still say, well, the integral will be from a to b of the g function times your delta, which is the thickness of the infinite rectangle that fit underneath. And the thickness of each rectangle is infinitesimal, so you let that thickness go to 0 theoretically, which is what the limit does. But I don't want you to think too deeply about that. What I want you to think about is dx is just the thickness, g is the function. Okay, that's all I want you to know. So this is still the length, and this is still the width. Okay. Number 3. But now let's say we put these two functions together. Still, I'm trying to draw them exactly the same. This is still g, and this guy is going to be, let's call it still the same one. So it looks something like this, right? So what we wrote earlier for f. So this is a, trying to keep it the same. Okay, so we said from a to b. Okay, so the top function is the f, and the bottom one is a. So I'm trying to graph this so you know what I'm trying to do here. This f is the same f over here. This g is the same g. So I'm just putting them together. It's just that I can't draw very well. So the integral from a to b, if I want to find the area between two curves, you have to subtract the top function f minus the bottom function g times delta. So this is now the length, and this is the width. Okay, so the area between will equal to third in basic terms, so we all understand this, is top function minus the bottom function. Okay? Does that make sense? How you set up the integral? Let me know before we start doing examples. This idea needs to make sense. Is that weird?
No, I got it.
All right. So this is an example. Okay. Example. Find the area. This would be like your homework. Of the region. So again, you're gonna have to be able to graph these, or use a calculator to help you out, or you can use Desmos too. Divided by the graph of y equals x squared plus 2, y equals negative x, and the function or the graph x equals 0 and x equals 1. Okay, so we have a bunch of graphs or a bunch of functions or whatever. Who cares? Okay, so here we go. Put 1 right there. We'll put 2 right here. This is 1.5, I guess. This is 0.5. Okay. This will be 1. 2, 3. Okay. So let's graph each one. We know this is just a basic parabola, right? But these vertical lines are gonna be part of the bounds. So let's graph those guys first. So I know I'm gonna have vertical lines at 1 and 1 and 0. Right, so they're gonna be right there. Now this is a parabola, so let's make a big table in case you have issues graphing. Next, over here I'll put the parabola, and the next one I'll put the negative x, right? So if I pick 0, this is gonna be 2, right? 0 squared plus 2. Plug in 1, that'll be 3. If I plug in 2, that'll be 4 plus 2 is 6. If I plug in 1 over here, that'll be 0, negative 1, negative 2. Right. Okay. I probably need some points in between, so let's choose 0.5. 0.5 squared would be what? 1/4, so 0.25, 2.25, negative 0.5. Of course, you can use your
question.
calculator. Yeah.
So here, first the under 3 is a 6, like 2, 3, 6. In the middle column, is it 2, 3, 6? No.
Yes. 2, 3, 6.
Okay, one more question. Why we choose this y, the x squared plus 2, this y to substitute in it with the two x's, the x and negative x? Why we choose this y?
Are you wondering why I chose these x values?
No, the middle column, x squared plus 1. Why we choose to substitute in this one, not the negative x?
Yeah, I'm doing that over here too. Doing both.
Okay. Doing both, and we substitute by a value of x equal 1.
Yeah.
Equal 0.
X is 0, 1, 2, 2.5.
Okay, thank you. Got you now.
So these are the ones I chose to plug in, and then I put the outputs right here. So try and do it all in one little place so it
yes
doesn't get messy.
Thanks a lot.
So then 0, 2 is right here, right? If I plug in 1, that's going to be 3. So the parabola is going to be doing this stuff, right? I don't really care what it does over here because it's bounded by 0. Now let's look at the line. At 0, I get 0. At 1, I get negative 1. Doesn't really help me, but that's all right. I'm gonna have to put some more points down here. So that'll be negative 1, negative 2. So plug in 0, I get a point here. So I plug in 1. I'm sorry, that's not true. I'll do that again. If I plug in 0, I get 0. So that's going to be this point. If I plug in 1, I would get negative 1. So that would be over here. There we go. That makes more sense. So I'm only using the points that are bound. If you're wondering, like, why did I pick those specific ones? It's because I can graph the entire parabola. I can keep going if I want to. But I don't care about the left side. I only care what's in here because this is where it's bounded. So I'm not gonna choose things above. See how I chose 2 and it didn't really help me? It's pointless to use this one. This one was stupid choice by me, right? So I need to choose things within these bounds. So my rectangle lives in here, and I need to find the area of the graphs, this graph between these two graphs here. Okay. Now, if you're not good at graphing, let's use a grapher together. Maybe this will help. Right. So hold up. Get rid of all these examples from earlier. Okay. Okay, you guys can see the graph, right?
Yes, sir.
All right. Can you still see it? I maximize it. I don't know how it changes on your end.
See it.
Okay. So I'm gonna graph the first one, the parabola. X equals x squared plus 2, right? So it was. Oh, we can call it. Yeah, that's fine. Who cares? Next one will be negative x. Next one will be x equal to 0. X equal to 1. So the black one is a 0, right? So I only care about this section right here. You see how the 4 functions bounded all this, right? This is the area that I'm interested in. Okay. So that's why I chose the numbers. I mean, if you couldn't see the functions by looking at them, then it seems difficult or seems weird how I just chose these numbers here, right? But if you're not good at graphing, then graph them somewhere else, like I did over here, and then go through it and say, okay, well, my integral will be from 0 to 1. The top function is the parabola, bottom function is the line, right? So you would start the problem and say integral from 0 to 1, top function, x squared plus 2, with some brackets here, minus the bottom function, which is a negative x. Everything times the x. Okay? Does that make sense? How you set it up?
Yes.
Yes.
So once you have this, you just integrate like you've always have, and you have the area between two different graphs. So the area is actually going a little further now that I think about it, right? It's down here. It didn't say y equals 0, it said x 0. So it's all this chunk. Okay, so the rectangle actually goes down here. So
We graph the x squared plus 2 and then the negative x, right? That's what we graph.
yeah, so what we graphed was the parabola, x squared plus 2, and the negative x. And then the lines on the side are x equals 0 and x equals 1. Okay. So
And
another way,
we choose the x 0, 1, 2, and a half to be close to the values that's being given for the x equals 0 and x equal 1 to be around those values?
yeah, I was trying to choose the edges of the bounds. So I chose the 1, I chose the 0,
Okay.
and I chose one in between.
Okay, one in between.
Mm-hmm. So if you know where you're stopping, you should plug that into both functions. That way you get these important points.
Yes.
Right?
Yes, that's right.
And then once you have those, you know what the top and bottom is. Another way that people think about it is they draw once they draw the region and they shade it, they just think, okay, the top of the rectangle minus the bottom of the rectangle. So you just draw it yourself. Doesn't matter where, but the top will be here, top function minus the bottom function. So this is the top, this is the bottom. Okay. So here we go. 0, 1. Minus minus, this will become x squared plus x plus 2, right? Dx. Integrate this guy, you will get x squared over 2 plus, oops, not cubed, plus x squared over 2 plus 2x from 0 to 1, right? Then you do your fundamental theorems, calculus stuff. So this would be 1/3 plus 1/2 plus 2 minus plugging in 0, which will be 0. And we get our answer, which is, I don't know, what is it? almost 3, but not really. 2, 6 plus 3, 6 plus 12, 6 going to be 2 plus 3 is 5 plus 12, 17, 6. Probably. But anyway, who cares about fractions? That's not important. What's new right now is, can you determine what the top and bottom functions are once you draw your region? Can you set up the integral and choose the correct bounds, 0 to 1, which is the edges of the region? And then can you do your basic integration? That's what matters. Does have any questions on any steps here? Pretty sure it's 17, 16. Yeah, that is. Okay. All right, let's go do another one. The more we do, the better, right? Okay. Same question. Example 2. Find the area between the graphs. And here are the graphs. Y equals x squared. Y equals 2 minus x squared. Between 0 and 2. Okay. So if you don't want to graph this by hand and you feel like that sucks, that's fine. No, I'm not gonna get mad at you. What you can do is just graph them first and then get an idea what the heck is happening, right? So you can say, all right, well, I know what it probably looks like. Let's go ahead and do it. And then I know what y equals 2 minus x cubed looks like. No, squared, not cubed. And I can see the bounded region, right? But they said between 0 and 2. Between 0 and 2. Let me double check something. Okay. Yeah, that's what they said. All right. I want to make sure I didn't write anything correctly. So the idea is I'm going to have actually a couple of different areas. Interesting. So 0 to 2. I have this section, and then this slice here before the 2. So we should probably do this. Even though they didn't tell us, this will probably help us see what's happening. So I have this piece, and half of this little egg circle thing.
I don't see what you're talking about.
You see it or no? Oh, shit. Forgot to share. My bad. So, all right. So I've added the purple line here. So I have this region, this lower region, and then half of this little oval. You see what I'm saying? So I have possibly multiple integrals to set up because it said 0 to 2. So that interval makes it really difficult. Well, I don't want to say really hard, but it makes it harder than the last question because now I need to make multiple pieces. You see what I'm saying? All right, I'm going to go ahead and
That's on the graph you're talking about?
yeah, so the graph shows you that. I guess this is what I want you to understand real quick one more time. I need you all to see this. So remember how we said it has to be top minus bottom, right? To make when you create the integral. But check what happens from right here. The green one is the top. But after that, it's changed, right? Something has happened. And then over here, the top has changed. So there's a couple of issues. Okay, so hold on one moment. Okay. So you guys know what it looks like now, right? No big deal. Okay. All right. Now the parabolas look like this. At 0, let's go ahead and do what we did last time. I think that was helpful. Here's my x's, here's my parabola, and here's the other parabola. I choose 0 because that's the beginning point, right? This one is 0, and this one is 2. So plug in 1, I get 1, and I get 1. If I choose 2, I get 4, and I get negative 2. You cool with me skipping the plug-in in part? Or do you want to know where these numbers are coming from? I want to make sure you see where the numbers came from.
So we're getting from the numbers were from the bounds from 0 and 2, and then you're plugging it back into the x.
Yeah, you're just plugging them in here. So plug in the 0, 1, 2, 0, 1, 2, and then you get these outputs. Okay, so let's go ahead and graph it. 0. Let's do the x squared first. 1 and 2. All right, so here's my parabola. It goes on forever, but I don't care what happens after, because the restriction was 0 to 2, right? Now the next one, also, this one's going to be 2 over here. When it's 1, I got 1. So they intersect here. And when I chose 2, I got negative 2, right? So that'll be here. So the other parabola is going, let me scratch this real quick. This way. Missed the circle a little bit, but oh well. So what we're going to do to make this a little bit easier is to only find the area between here and here. Because finding this piece, can't really do it right now. Because we're going to do between the curves, so only these pieces. Use my red pen here. These guys. Okay. So we're going to have 2 integrals, one from here to there, then another one from here to here. Okay. That's how I want you to think about it. So the area for this graph will be the integral. So let's break it up in 2 parts, 0 to 1. So from 0 to 1, what is the top function?
X squared.
Gonna be x squared, right? Minus
minus 2 minus x squared.
minus 2 minus x squared dx.
Plus
So that's one piece. So now we're gonna have to do plus
-1.
all right, 1 to 2. Okay, so we're doing 1 to 2. So now from here to here, what's on top?
Like 2
2 minus x squared.
Yeah, 2 minus x squared minus the bottom x squared bracket. Gotta be careful with my parentheses because if I don't put them, it's gonna come out messed up. Okay, so now we can calculate the area between the curves, even though the area is separated into two different sections, right? So we're gonna get
2
0, 1, x squared minus minus will be plus x squared minus 2. Combine that in a minute. 1 to 2. This would be 2 minus x squared minus x squared. We're going to combine everything. 0 to 1. That'll be 2x squared minus 2 plus 2 minus 2x squared dx. So you guys still with me, right? Does this idea make sense? The setup?
So the last x is on the second bracket was x squared also? 2 minus x squared minus x squared.
Yeah. So this one was a positive, right?
Yeah.
So it becomes minus minus negative.
I was just trying to see, 'cause I didn't know it was a 2x squared. I mean, x squared.
Yeah, so it became 2x, negative 2x squared, and up here we had a minus and then another minus.
Okay.
We combine. Mhm.
Okay, I got all the substitution and I got the graph very well. The only thing I didn't got is the point number a equal this equation. How you get that from 0 to 1 at the first portion, and how to get from 1 to 2, and how you choose the first x squared. Again, first step only again.
Okay. So this is why I chose these numbers, right?
Can you put the paper down a little bit? Because I'm not seeing. Yeah.
So this portion, this region, changed
Yes.
after 1. So you remember how you said the top and bottom are shifting, right?
Right.
So after that, so I had to create because it changed. I had to start after that and switch this. So
Okay.
I chose to start over after 1 and choose the new top and bottom functions.
Yeah, I can see that. Okay, and how we choose the x square minus 2x at the first one, and the 2x minus x square in the second one. How inside the integral, how we choose the x square to be the first part.
Yeah, that depends on where it's at, right? This is the top and the bottom between 0 and 1. This is the top between 1 and 2.
Oh, yeah, I got you. Okay, I'll put this down. Thank you.
So that's how you choose them and set it up. Once it's set up, we're back to chapter 5, right? This is the stuff you should be better.
Right.
You should know this at this point.
Yes.
I hope.
Yes.
I hope so anyway. But we'll see.
Yes.
I'm gonna do the integration. That'll be what 2/3 x cubed minus 2x from 0 to 1 plus 2x minus 2/3 x cubed from 1 to 2. And then after all that, all those number things, you're gonna get 2/3 minus 2 minus 0 plus 2 times 2 minus 2/3 2 cubed minus 2 minus 2/3. So anyway, you guys know how to plug numbers in. I'm not going to worry about all of that. The answer will be 4. When it's all said and done. Is there any part that bothered you, or do you want to see more steps here? Or the main important part is the setup. That's the new stuff. Does that make sense?
Set it down. It's not that hard. I don't have that problem. It's just the graphing portion. That's why I'm having the problems with it.
I understand. I did too when I took this class, because graphing was back in college algebra, and yeah, I haven't done it in a while, or maybe even before that. These questions feel a little bit harder because your graphing's rusty. But if you're welcome to use those graphing tools to help you out, right? If we go back to our calculator, let's look at it. My teacher didn't let me use it, but that's cool. Let's see here. Sure.
Graph it on the calculator and then just...
Yeah, you graph on the calculator and you're like, okay, well, I can tell that from 0 to 1, that's the top, that's the bottom. 1 to 2, it's switched, right? And that's it. Just find the integral for this part and the integral for this part. And the intersection points can be found by just clicking. So you can say, all right, I know it's 0 to 1 there. Yeah, there's 2, of course. So using this to guide you to set up the integral should make it a little easier if your graphing is rusty. Oh, I just saw your question. Mohammed, do you still have that? Do you still have that question? I don't know. Yeah, you just sent it. Okay. Yeah, so the idea, right? Remember, the top function switched after 1, right? So at the beginning, this guy is going to be on top. But then after 1, it's at the bottom. So I had to switch and create 2 separate integrals. If it stayed the same, if like on the other question, you remember over here, the top stayed the same the whole time. So I didn't have to make 2 separate integrals. Okay. So if it stays, if it's consistent, the top is the top and the bottom is the bottom, then you're only gonna have 1 integral. But over here, we had a transition from this top function to becoming the bottom. This bottom function became the top. So when that happens, you need to do separate. Does that make sense?
Yeah, I guess.
So far, all the examples were vertical using the x values. It could be a horizontal rectangle, because when you're graphing these, you can't have the rectangle hit the same graph more than once. Like see how it hits both, hits one or the other all the way down. For example, if I were to try to find this area down here, it would hit that same, it would hit this function and then hit this function multiple times. So sometimes you need to switch to dy to help you. So let's do one of those guys and write some notes right beforehand. So the general idea is making sense. So let's formalize everything into the big picture. So finding area using vertical rectangles. So we said area will just be some x value to another x value with the top curve minus the bottom curve, right? So we kept saying. And then that would be dx because it's vertical. So if your graphs are something like this, you have a rectangle like that, that's dx problem. Okay. Now, for a, let me write the title here. Finding area using horizontal rectangles. A will equal the integral from y1 to y2. This time it's going to be the right curve minus the left curve. Dy. So if you notice a question that you can't do vertical triangles or rectangles rather, then you need to switch to horizontal rectangles. And if you switch, then that means you need to change the function into dy. So if the question gives you x stuff, you need to change it to y. Okay. Let's see a good example here. This picture would be something like this. So you have a graph going doing this kind of thing. Then you have another graph doing this. And I wanted to find this region. If I were to draw a rectangle horizontal, vertically, I would hit the parabola twice. You see that? But if I were to go horizontally, I would only hit each one time. Okay. Yeah, well, let's just start a question because that looks too ugly. Let me give you an example, a better one. Okay. And let me write another note. For x1, y1, and x2, y2 are intersections. Intersections of the graphs. So the points where they intersect. Okay, so let's do an example. Example 3, I think. Find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. So these guys were nice enough to solve it for us. Okay. Solve for y, that is. So let's go ahead and get a picture of this. So we got x equal to 3 minus y squared, sideways parabola. We have x equal to y plus 1. Right? So here's the issue. So the bounded region looks like it's going to be right here, right? So if I were to go vertical, it would work out from here all the way to here, right? See how I'm hitting the top function, bottom function, top, bottom, top, bottom. But then I get to here, and I'm only hitting the same function, which I can't do that. So if you notice that happens when you're drawing your little rectangles, that gives you a clue that no, I can't do vertical. I need to go horizontal. So I hit right function, right function, all the way down. It doesn't change. You see how right and left is going to be better? So you need to be able to identify, when do I do dx, when do I do dy? When is it horizontal? When is it vertical? Okay. So looking at that graph, I want you should be able to see that that is a horizontal kind of question. This one is obvious because they software export. But sometimes they're not going to do that. You're going to have to software export yourself and then find the intersection points. If you did not have a grapher, let's say you did it all by hand, you would have to set these equal to each other to find intersections. So to find the intersection points, set them equal to each other. Since they're both solved for x, that means I can do this. 3 minus y squared is equal to y plus 1. Solve for y. I'm going to move everything to the right. So that'll be y squared plus y minus 2. Factor. That's how you solve quadratics, right? That would be what? Minus plus 2 minus 1. So my intersection points. So y equals 1, y equals negative 2. So I'm going to be integrating. We'll look at our graph again. If you're wondering, like, why do I care about these points, right? Because of this. And I set the functions equal to each other. So now we'll find these values, right? We found y equals to 1, y equals to negative 2. So using this grapher, I know those values, right? dy, I'm going to integrate from negative 2 to 1. Since I'm doing dy, I'm looking at the y value. How low am I going? Negative 2 all the way up to 1. You see that? So the horizontal rectangles start at negative 2 and go all the way up to 1. Y value. Okay. And that's what this helps me find. Negative 2 to 1. So the integral will be, right, negative 2 to 1 on the horizontal, on the y-axis, right? Now I'm going to do the right function minus the left function. What is the right function? Do you remember?
Three minus y squared.
Yeah, it's the parabola, right? 3 minus y squared minus the left function, which is the line, y plus 1, dy. Okay. Try to draw my little picture over here. So we had 2, 1 point there. We had another point at -1, -2. So that would be over here. We had this line going on like this. I'll give you guys a picture, and then we had the parabola doing some nonsense like this. Something like that, right? My picture sucks, but oh well. So we are curious about this little region. Okay. So we draw the horizontal rectangle, right? Right minus left, right minus left. So I'm going to draw infinite rectangles, horizontal rectangles. That's why everything needs to be in terms of y. If I draw a horizontal, that means I'm doing dy because the thickness of the rectangle, right? The thickness is now in terms of y. So everything needs to be in y. If you're choosing a horizontal, you better not have any x's in here, right? That doesn't make any sense. You need to convert yourself. It's not already converted for you or solved for you. Is there any questions about this setup? It's the same stuff, it's just in using the y instead of the x.
We don't, we subtract them, right? Because it's a y, right? Not, it was the x, we add them, right?
No, they're both subtractions. This is like kind of like your formulas right here. The top minus the bottom, but if that's for dx. For dy, we have the right minus the left. Okay, and these bounds are chosen by the intersection, y1 to y2 or x1 to x2. Those are chosen by the intersections, where the graphs intersect. Okay, and they intersected over here. Let's look at the picture, the pretty picture. They intersected here and there. So that's my y1 and y2. Okay.
I have a quick question.
Yeah.
The area above that linear line, we wouldn't add that area to it as well?
You're talking about up here?
Yeah.
No, because they're only asking for the area that's bounded by the graphs. So this area is technically unbounded. Because
Okay.
this parabola goes on forever, right? It's an open space.
Okay.
Unless they told me outright, oh yeah, it's also bounded by the y-axis, x equal to 0. But then I'd have to do 2 separate chunks, this section and that section.
Okay. Thanks.
Yeah. So just read it carefully and find out, okay, what section do they want? Do we want multiple sections, one section? And how do I approach finding the area of that specific section?
I have a question here.
Uh-huh.
So when we make the equation equal 0, in this way we get the x, not the y, right?
You're gonna solve for x or y the same way, but since I'm doing everything in y, these are the y values.
Ah, okay, got you.
But the way you solve it is gonna be the same.
Got you.
Like if this was all, like for example over here, the last question, I could have set both of these equal to each other and solve for x, right?
Yes.
And then I would find the intersection points. I would find these guys right here. When you solve for it, you would find that one. There's only one intersection point, so setting them equal to each other gives you this point. But since they told me 0 to 2, I didn't have to worry about finding other intersections or other bounds, so that would have made it a little easier. And over here, they didn't intersect at all, so they had to tell me a bounded region. 0 and x equals 0, x equals 2. They had to close it off. So it really depends on what's happening. But the strategy is the same. Remember, do dx if the rectangles only hit the graphs once. All right, but if you see, like on this picture here, if you see the vertical rectangles hit this twice, then that's a sign you don't use vertical. Okay. Or if you're doing like horizontal and then you hit the same graph multiple times, then you wouldn't do it either. Like this one. Let's say I wanted to find this region, right? I would not want to do dy because I'm hitting the blue parabola twice. So you would choose dx because I could hit each one time. Once for every rectangle. An infinite number of rectangles. You see the idea?
Yeah, I see it now.
Okay. So, 920. All right. So let's move on to the next part. I guess we can start the next section. I don't know if we can finish it. So that should be good enough for 7.1. All right, so the next section is about volume. So the approach that we just did is going to help in 7.2. It's just we're taking it a little bit further. So basically, the idea is going to be, I don't know, let's look at a simple one. Yeah. Let's look at this one here, this first one. We understood how to find the area, correct? But let's say you were to spin this around the, I don't know, spin this around some imaginary axis, right? It would create a 3D object spinning around. Imagine like an after image or like a shadow or something. So as it's spinning and spinning, it creates a solid. So if you find the area and multiply it by that spin, you will find the volume. Now that's the big picture idea for the next section. So if you can find the area, then we can tack on an extra piece to find the volume. Okay, so let's start with some easy questions first and write down the idea. Okay. So 7.2. Volume. Slicing discs and washers. Okay. One moment.